Silafon around Indian berries, even right at the ones that are killing $1 million. And so I should with me some essential structures. It might be hospital, might be the school buildings, might be anything. Um, so we need to carefully gone through all the design process. So that means that's a part of the engineer. Engineer will do that. But while they do the design things, they also require a the the ground motion record at that particular site. Right. So basically, if they have that ground motion record at that site, then that will be much more easier for them to simulate that ground and try to design the structure based on that simulated results. Right. Now the question is this, that the earthquake has not happened or will not happen at every places. Or even if it happens, maybe at that point there is no record available. So that means there is no physical record available. So that's a challenge, right? So what will happen? We need to uh, simulate that ground motion at that particular site. So that is required. Now the question is, this simulation uh, is a very complicated work, because in a engineering analysis, we require a high frequency ground motions. High frequency ground motions, I am talking about between 1 to 20 hertz frequency range. That is what minimum required, because otherwise it will be very difficult to do the design if it is if the engineer likes to really do some seismic analysis on that. So what they need is that ground motions. Now, computationally, that high frequency ground motion generation from the time domain data, so that means from the any near about fault surface, and then have that particular earthquake to happen, and then take that earthquake, propagate it through the earth, and then come to that particular site. As I told you last time, these are all convolution operation in time domain. And whenever this is a convolution operation in time domain, it's a very complicated work. Okay, because all the layers underneath the earth will be refracted. So the time domain analysis takes a lot of time, and then we also need to know very accurate information of the velocity for each and every meter, or might be that type of information is required. So it is very difficult to quickly achieve it. Okay, if you can achieve it, but even if you can achieve it, you cannot go beyond 1 hertz. 1 or 2 hertz you can maximum can go. You cannot go it is beyond some, even if 5 hertz, right? So high frequency is very difficult to achieve. Now, what alternatively we can do is a stochastic analysis. Now, the stochastic analysis is basically for a high frequency synthetic ground motion generation by using the spectral data, right? So that's the high frequency part. So that means from 1 hertz to 20 hertz, whatever you like to do, you can do that, right? If you have the site information available. Now, so usually, if you have a very nice computational team, they can do some of the hybrid analysis. So hybrid analysis means the low frequency part, they do it by time domain modeling, and then high frequency part, they do it by the stochastic modeling, and then they superpose it on each other and generate a broadband type of ground motions, right? So that's usually the people, those who are seismologists group, they usually do that. So today I will be give you some glimpses of how to generate a stochastic ground motions, right? So if you are working with some engineering community and try to generate a ground motions based on the realistic ground earth information, then it will be very easy and it will be quickly to be generated, and only you require two information. That means the distance of the site from the source. So that's the information you need. It might be the epicentral distance. So that information you need, plus you need a information about the magnitude of the earthquake, right? So magnitude means it's a MW magnitude, or the uh, moment magnitude values, MW. And if you know the MW, then as I have told you last time, that MW can be related to M0 by a relation. So that M0, if you know, and your distance you know, then with some of the measured parameters of that area, you can easily generate a synthetic ground motion of any magnitude you want. Right now, so this process is known as a stochastic generation. Today, I will be doing, or I will be showing it only for a point source, right? But this point source can be extended to a extended fault. That is also possible by doing some summation over the point source. So that means if we assume the point source at different points, and from each one they are releasing the earthquakes, and then you can all superpose it, then that will be an extended type of information, or extended fault line, or we call it as a finite fault model simulation. So that is also possible, and that can be also done. And but I will be today first touched upon the point source. So if you understand the point source, then it will be very easy to calculation. So that means there is no reflection things. There is no coming up any sort of wave propagation. Wave will be only passing through the through a straight line, and then it is being generated there. So the entire Earth model will be only used as a one particular thing. So there is no layer present in the system, right? So that is your stochastic things. Okay, so it is stochastic ground motion simulations. Okay, now let's. So this is whatever I am trying to tell. The challenges with the physics-based ground motion simulation for greater than 1 hertz is very problematic, because it requires a lot of information in order to generate the 1 hertz type of accurate informations, right? But for our engineering purpose, we require the frequency range about this much, 0.01 to 10 hertz type of things. Okay, so now the stochastic simulation is done in a frequency domain, and then it will be converted back to the time domain. So we will be doing all the calculation in the frequency domain first, and ultimately end up the result, because we know the time series data, because we have to work with the time series data. So we will be coming back to the time series model. Okay, so the time domain. So from the frequency domain, we will be going back to the time domain. Now, in a frequency domain, if you try to see in a frequency domain, whenever you are seeing it, that will be that will be basically the observed record. If you see in your recorded data, then if I can call it as a Y, so Y is a observed spectral data at the recording site, right? So this observed record, if you take the observed record and take the Fourier transform of it, then that will be dependent on the magnitude of the earthquake. That means the M0 value, the distance of the earthquake, and also the frequency of that things, right? So this is the functional form of any observed record or observed spectral data, right? So now, if you, as I told you last time, that this recorded data at your recording site is basically a convolution product of source, path, and the site, right? So this is a convolution product of source, path, and site. And I have shown you in our frequency, in our Fourier transform domain, that the convolution in the time domain can be interpreted as a multiplication in the frequency domain. So it is basically the source spectra. So this is your source spectra. This is the source spectra. This is the path spectra. Spectra. This is the site spectra. And this is the instrumentation factor. Right? So this is the instrument factor. So instrument spectra or instrument thing. Now, what is the instrumental factor? Because on the ground, you might have a displacement meter, you have a velocity meter, you have a accelerometer. So that three sensor will have a three different type of response, right? So that factor will come here, and that is what we are seeing it as an observed record. So any observed record is basically multiplication of these three. So first, source has to produce the signal in the spectral domain or spectra, and then that spectra will propagate through the path one, and then it reaches to the near site, and the near site will get amplified, and then the whatever instrument is recorded, it's recorded that. Up to this much, everybody is clear. So now, so the source spectra is related to the how big will be the earthquake. So that means it will be related to the seismic moment of these things. So this is the moment and the frequency part. The path, wherever it will be going, it will be basically R and F. So that means the distance it travels and the frequency it goes. And then the site is also frequency dependent part, and the instrument is also frequency dependent things, right? So these are the things you can understand. So therefore, this is the source spectra, and P and G, if you multiply it, okay, if this product, P and G product, this P and G product is basically the what we call it as some sort of a green function. We'll come to that point afterwards, not necessarily need to know. Now, I told you that our moment magnitude MW is related to M0 or the seismic moment by this relation that we have already learned, that MW moment magnitude scale is related to this one, and as you understand from here that the different magnitude level, say suppose this is your 5 magnitude level. I told you how a spectral character or a spectral things looks like. So this is the theoretical spectra, if you use your just your moment and the distance things, it will looks like this way, right? So it depends up. So as you say, as the magnitude increases, the spectral level will jump up. Okay, so the Fourier acceleration spectrum, it will be more or the high value because magnitude is high. And if you see the basically the corner frequency, so that means this point here and this point is one here. So that means as the frequency increases, the corner frequency moves towards the low frequency side. So as the magnitude increases, corner frequency moves towards the low frequency side. So a pictures, but these things are all same, right? So this is basically, we call it as a F max, maximum frequency. After that, they will attenuate. So it will be rise, then it will be flat, then it get attenuated. So similarly, this will be rise, then this is a flat, then there is a attenuated, right? So this is your theoretical spectral shape for any earthquake. Now, so if you see that in the actually, if you take a record and then take the Fourier transform of it, uh, you will be seeing some of the noise, right? So that will be there because it is like this, right? But the shape will be in this manner. Is it clear? Hmm? So therefore, if I can understood that what is the magnitude, I can tell what will be the moment, right? Because there is nothing many problem. If I give a 5.0, then this moment I can easily calculate M0 value. And if I can give it my 7.5 or 8.0, I can easily calculate the moment, right? So the M0 value I can calculate. So that M0 value will be the basis of this right? So the amplitude spectral level will be up, right? So now let's see that um, this M0, as you have seen it here, this M0 and this FC, they have some relation because this is actually decreased by this way as it moves, right? So M0 and FC, there is a relation. So that means as your FC and M0 are inversely related. So as the M0 increases, FC will be decreases, right? So so we are trying to do a modeling which is called omega square modeling. So omega means it's a 2 pi f. So omega means it's a 2 pi f. So basically what will happen that it will be raised by the omega, then becomes omega squared, and then it will be decay by the omega square law, right? So that's your main factor. So it is what we call it as a omega square model, right? So that's the omega square model will be always implemented here. So that means it will be raised like this, become flat, and go like that way. So M0 FCQ is equals to the constant. So that's your main relation between M0 and FCQ. So if you know from your MW value, the M0, then from that M0 value, now you can calculate what will be the FC values, right? So that you can calculate. Now, it can be theoretically shown and or mathematically it can be calculated. For a point source, we are talking about here, always this information is for the point source. Point source means, what do you mean by point source? The point source is this, that from the site, the source is little bit away. So that means, what is the little bit? Around 50 kilometers or around this kilometer away. So that the entire source, we can we can approximate it as a point. So that means with respect to a further um, site, this entire fault rupture can be approximated as a point. So if it's the point source, this thing is valid. But as I told you, this point source model can be very successfully applied to as a extended source model too. Just only it is money in another loop, I will be repeating it for the different point on the space and then add them together. So that's the only thing we have to do. But let us not complicate this. Let us first understand the point source, and then we'll be doing that. So your F0, it will be actually calculated as a 4.9 to the power 6 beta x into sigma delta sigma by m0. So this is your constant term. So this beta x is the shear wave velocity. Okay, so this is your shear wave velocity and near the source. Okay. So S stands for it is a near the source shear wave velocity. So whenever it gets ruptured at that point, whatever is the velocity of the shear wave, we are doing that. Now, there is another thing I like to point it out here is this, that this entire simulation is only for the S wave portion. So that means the shear wave portion, because we are not interested to have a P wave to be modeled, because the P wave model, as you have understood, that it's a very small motion, and for a building or a structure, the P wave will not do a much more damage, but the S wave or the shear wave does. So therefore, the stochastic simulation is for the S wave portion of the data. Is also there is a shear and there is a longitudinal part. So we will be doing only the rally wave portions, right? So that's the part where the shear motion is basically predominant. The frequency content of the wave and the amplitude of the wave, these two factors are necessary for a engineer to design the things. Engineers do not need to know, or they have never read in their course curriculum the phases of the waves. I'm just joking it, but the question is this, that they only need to know for the design purpose, they only need to know what's the frequency and whether that frequency can put the structure in a resonance or not. That they try to prevent by their design practice, and also the amplitude of the thing. So these are the two things they require. So if you can provide that information to them, they can easily model the structure and model the ground. The interaction of the ground and the structure can also be calculated by that. Okay. So we had found out what will be the corner frequency F0 value for this one, right? So another part is this one. So this is what we call it as a stress drop. Okay. So delta sigma is the stress drop. Now, this stress drop is we call it as a stress parameter. It will be, in this case, it will be basically from 0.1 to 100. This could be any value between this one. In general, we can take something around 10 megapascal MPa. That will be fine for our modeling purpose. But we have seen a lot of record, and most of the cases, this value is between 0.1 to 200 MPa. But on an average, the 10 MPa values, assuming the 10 MPa for your simulation, it will be fine. So put that delta, this is a 10 MPa in bar, and then M0 will be the seismic moment in the dyne centimeter. So please remember that we are giving the BS value into the kilometer per second. So these units are very important. So keep this unit in mind, that you should not give a different unit, then it will be difficult things to calculate the range or the calculate the spectral values. So this has to be in hertz, and the beta has to be in kilometer per second. Stage drop is in a bar, and then the M0 will be coming as a moment in the dyne centimeters, right? So these are all a mix unit of a CGS and MKS unit. So that you need to keep it in mind. Okay, so so this is what we have seen, that if it is a that means the twofold of change in the delta sigma values, only can lead to a 1.26 time of difference of F0 value. So delta sigma value has a contribution, but that contribution is not a very big contributions, right? But we can give a value 0.1 to 10, any range. It will not drastically change the amplitude level. Okay, so now let's do term by term each factor. So that means source factor, path factor, as well as the site factors, right? So these will be doing one by one and try to see these things. Now, if you do the source factor, as I told you, this is your M0 into F. So this is the function of M0 and F, right? So M0 and F, this can be written as some constant value C. Then the M0 is actually the moment values. Then there are two terms, is a SA and SB. So these are what we call it as some sort of a shape. Okay, so this is your shape factor. That means how the spectral shape it will be. So that will be the shape factors. So this is your CM0 and these two terms, right? So these are the shape factors. I'm going to show that how it will looks like this way to this way, or how it will be, the shape will be looking like. So that shape factor will be defined that, and these are the amplitude it will calculate, right? Now, so this C value, it is a constant value, okay? And this constant value, it is given by a expected values of r theta phi. Don't get confused with the r theta phi, because it might be a very big thing. No, it is not a very big thing. It's a number for your because as you understand, whenever there is a source is rupture, that source when rupture, it will rupture the S wave as in a different different type of radiations, right, from the source. So that factor will be taken into the account based on your theta and the phi. Phi is the azimuth, and sorry, the takeoff angle and the azimuth. So that's the two factor. And for the S wave, this r theta phi is more or less constant, about 0.55 to 0.6, right? So that's your number. So let's take 0.55 is the number, just only take that value. Then V is the V is the partition factor. V is called, it's a partition factor. So partition means what? It is called partition factor. So partition factor means whenever V arrives at the site, it will be split into the two components, right? So one, because there are two horizontal components on which S wave is more predominant. So, but we are only calculating only one component, right? So we are not doing both so we are treating both the horizontal component as a single component, right? So that will mean that is why we are basically using a factor of 1 by root 2, right? Because if we have a east to west motion and north south motion, so this is 1, this is 1. So we are taking it as a root 2, 1 by root 2, 1 square plus 1 square equals to root 2. So that is, so basically we are calculating the resultant one, so not the individual ones, right? So that V, when therefore partitioned it into 1 by root, right? So V is 1 by root 2, and F is the free surface effect. So that means S is equals to 2. So F is equals to 2, and and F is equals to 2 because it is a free surface, uh, because this recording station is on the surface. So here is the air, and here is the material, right? So these are the two things. So it comes, the waves comes here, and after that wave has to return back. But if the station is located inside the earth, or that means, or you are putting the station in a borehole and you are trying to generate that time series, then you have to calculate that factor. But if we are trying to be here, then it will be the factor is 2, because we are not considered anything has gone to the air. So therefore F will be equals to 2, right? And then this is your 4 pi, and rho S and beta SQ. This is the shear wave velocity at the source, and rho S is the shear wave velocity, the density at the source. So rho S and beta SQ are rho S is the density and beta SQ as the velocity of the shear wave uh, at the source, right? And R0 is the radius which we took as a 1 kilometer. So that means this is the source. So everything is calculated as a reference distance of 1 kilometer from the source. So R0 is equals to 1. So R0, 1, V equals to 2, actually V equals to 1 by root 2, F equals to 2, and then these two values are known, R0 equals to 1. So we can all calculate the number associated with the C, right? So rho S and beta S are the shear wave velocity at the source. So if you have a crustal earthquake, so that means the earthquake is located within the crust of the earth, then the rho S equals to the is something around 2.17 kilometers. Sorry, say 2.7 gram per cc, and Vs is around, or the beta S is around. Let me see, the rho S. Sorry, the rho S equals to the 2.7 gram per cc, and the beta S is around 3.4 kilometer per second. Right. So again, you can see these are all mixed unit. So it's a 2.7 gram per cc, and this is your 3.4 kilometer per second. R0 equals to 1 by, this is a kilometer, and R theta phi, these things are all numbers. So that does not mean, but so you need to be careful that you have to make it a proper conversion when you try to make it a particular unit, right? So, So that's the constant part, right? Then this is your M0, which you have already computed from the MW values uh, or the magnitude values, so that you can put it here. And then next part is these two shape factor, SA and SB, right? So there are a lot of research on that, what should be the shape, and there are a lot of scientists or the seismologists, they had prescribed various relation depending on the magnitude of the earthquake, depending on this one. So it could be a really complicated one. If you want, you need to read those numbers for a uh, for a particular interest of your simulation process. But in general and overall, this SA M0 and F is given as a 1 by F over Fa, and Sb is equals to, it is equals to 1, right? So these are the two factors we can, this one. Now this Fa, it can be calculated from some money relation. I am showing you this relation, the next page possibly, yes. So as I told you that that this will be the various model that can be used, or that the seismologists have suggested over the years by seeing the recorded the recorded data, and so that can be used. But we can use any relation which is a this relation is also a very good relation, FEA. That is also a very good relation for the FEA 96 model. That also have a SA value, this one, and this FA 1 by FA plus FA whole, this is your FA. This has been done by corresponding this relation, right? So if you can use this FEA, so you need to calculate this FA value. So FA will be equals to 2.63 into 0.5 m. So m is the magnitude of the earthquake, which is the MW values. So from here, that will be the log FA. So from which you can calculate your FA value. So we are calculating, so we know the magnitude. We can find out this number, and that will be equals to log FA. So from here, I can use the FA, and the F is the frequency, so that we can calculate this number. And then this value, we do not need to have a log B, because FB is not required, because this value is already 1. Make sense? Okay? So these are the things you can calculate from this set factor, and that you multiply with it. So from there, you can find out that this part of the wave, so this will be, whether it will be like this, or it is a sharp peak like this, or it will be this one. That is a question, and that is what we are trying to do. This shape, how the things are being coming from it. So this is your F value. So, and this part, it will be coming like here, how the frequency is changing in the F. So this is your F by FA, right? So FA value, you are trying to find it out from the magnitude, and that will be equals to SAMT. Is it clear enough to this much? All right. So you can calculate, right? So just a multiplication, there is nothing else here. Okay. Just only you need to remember that how to do this thing. So this rho S, beta S are 0, are unit in the gram per cc, kilometer per second, and kilometer respectively. Then C should be multiplied with a factor of 10 to the power minus 20, because you have to do all factor converted to a a CGS unit. So that's why you have to multiply it with a 10 to the power minus 20, because your M0 from that relation comes in a dyne centimeters, right? So that's why you have to convert everything in a in a CGS unit, right? So so that will be fine here. So we have you are free to choose any model, or might be you can check it out with a different model and try to see how this things looks like. Okay, so that's the part. Now, next part is the after the source part. So source part we have understood. It is a C multiplied by M0 into 2 step factor, and these are these numbers. So you have done it. Source part is gone. Next is the path effect. Now, path effect means what? The path effect is that if a shear wave or if a wave propagates, as it propagates through the medium, uh, it goes under a little bit attenuations, right? So there is a path. With the path, the wave get attenuated, and also their energy get decayed, right? Basically, because as you see that whenever you throw a stone in the pond, so the energy is concentrated at the point when it will be, when it has hit the ground, and when it hit the pond, and then it will be gradually spread out, right? So this is what we call it as a geometrical spreading. So this term is known as a geometrical spreading. So this is, so as it spread, its energy get attenuated, right? Because its energy will be less and less as it moves. Now, if you can see it here, on the very beginning, they will have a uh, they will have a fully circular type of things. But as it propagates more and more, it becomes a straight line, right? It becomes a totally a cylindrical form. So first it was a spherical form. Then as it propagates more, then it will be a very surface waves type of things. It comes into the pictures, right? So what will happen that we need to set this. So whenever it is a spherical, it will be decayed as a 1 by r square. The energy, because it is the spherical part is a 4 pi r square, so that will be divided as a 1 by r square type of decay. But as it goes much beyond, then it will be 1 by r type of decay, right? So it's a cylindrical type of decay. So what we have seen the lot of earthquake data, and we have calculated how much is the energy of that data is. So we had found out, in general, it has been noticed that again, it depends upon each sector or each region, but more or less it has been found that between, say, suppose 10 kilometers to something around 70 kilometers, the decay is 1 by r. Okay, and this is 1 by r. Then it is a constant up to, say, 1 by 70, and then it is being decayed, as a 170 into this way. So this is what we call it as a this path factor has two components, right? So path factor is a frequency dependent and a distance dependent, right? So because as it travels, it will have a more decay. So this has a two term. One part is the GR. So it is exclusively the distance part, and or the distance type of decay. And then there is another part, which is the KFR, which is the frequency and the distance dependent part. Now this GR will be equals to 1 by R. So say suppose your R equals to 50 kilometers and you have this type of model. So then you write it down, your GR equals to 1 by 50. Exactly like this, because R0 equals to 1. So 1 by 50, it is all equals to up to the 70 kilometers. You can directly write 1 by that distance, right? If it is a more than 70, so that means R1 and R2. If it is like this, so then we can change. Then GR1 means it is a 1 by 50 and 1 by 70, because that's your maximum value, 1 by 70, and then 70 by R. And then say suppose your R equals to 100, right? So then it is a 1 by 70 here. Then it is a 70 to the then it is a 70 divided by 100. Let's see, R equals to 100 to the power P1, right? So this P1 can be 1, P1 can be 2. So that depends upon how you are trying to measure it here, right? So P1 can be 0, 2. So P1 can be 0, P1 can be anywhere. So that P1 can be 0. So if it is a G, then it will be 1 by 70 only. So this will be 1 by 70 only, and then it will be going down like this way. And the next part, it will be this one, and then P of Pn, we can calculate based on the numbers, right? So this is this, and we are taking the R. R value is basically that if this is the epicentral distance and this is the H, then this is your R. So R is from the source to the site. It's a direct distance. So R equals to T square plus H square, right? So you know the epicentral distance, you know the depth of the earthquake, so you can calculate your R and then take the values accordingly, right? Okay, so this is your, this is, you can take 1 by R all throughout, but it has been found that after certain distance, since the wave shape changes, it will be much more better to use a different geometrical spreading. Okay, so with a P1 0.0, P2 is equals to 0.5, and so on and so forth. Okay, so that's the energy decay due to the spreading part. It's a geometrical spreading part. Then there is another decay is due to the attenuation, right? So due to the, because as the wave passes through the medium, they are selectively high frequency part get decayed, right? So that's your attenuation path. So path effect means it's a geometrical spreading plus there is a attenuations, right? So that's we need to also investigate. Now this KFR, that is what the attenuation part. This attenuation, we call it as an elastic attenuation. Anelastic attenuation is due to the material property. There is that due to the propagation, the material has a, say suppose water and all these things. So they, or the fluid, they might have attenuated the amount of energy, right? So that attenuation is due to the, and this attenuation, it has been found out that is a frequency dependent. So that means one frequency attenuate in a different manner to the other frequencies, right? So it is a frequency dependent attenuations, right? So it's a frequency dependent attenuation. frequency dependent attenuation. So that is what we were trying to model, right? Now, this frequency dependent attenuation is KFR, which is a part of this function, the P function, because it is a JR into KFR. So that part will be equals to e to the power minus pi f r. So this you all know. So minus pi is 3.14 into f is the frequency above which you need to calculate. And then this is your QF and this is your VQ, right? So PQ is basically the shear wave propagations, right? So you can take it as a 3.2, 3.4, or might be anything that will be fine. So, PQ is the propagation S wave velocity. You should not confuse with a beta S, whatever you have used for the shear wave velocity at the source. That is the shear wave velocity at the source function. But this is how the beta values is basically, or the shear value is basically propagating through the medium. That's a PQ value. And that value you can have it 3.2, 3.3. That will be the PQ value. So this is your PQ. And this QF, there is a new term you got. It's a QF, which is basically the attenuation, frequency dependent attenuation. So QF is basically frequency dependent attenuation factor. Because all other things are basically the distance and the velocity, these are the constant term. So only the F, it is a frequency dependent due to the presence of this one and the F values, right? Okay. Okay. So now, this will be, we need to know this number. Okay. Now, this number is a frequency dependent attenuation. As you see, this is your 1 by Q. So the Q actually, I have to tell you physically correct. This is we call it as a frequency dependent we call it as a quality factor. Q stands for a quality factor. Okay. So, and 1 by Q, F. So that means it is a QF minus 1. This is what you call it as a frequency dependent attenuation. Dependent attenuation. So this factor, you can see it here at around 1 hertz, we can give a particular value, and then after 1 hertz, it get decay, right? So it get decay. Now this will have a particular value at this point. So this is what we call it as a Q0. So Q0 is the attenuation at 1 hertz. And this is what we are plotting is basically Q inverse. So that means attenuation values, not the quality factor. So this is your attenuation is also a frequency dependent. So QF is given as a Q0 into F to the power N, or 1 by QF is basically 1 by Q0 into F to the power minus N, right? So this is a 1 by Q0 is the attenuation at 1 hertz. So 1 by Q, so this Q0 is basically the quality factor at 1 hertz. Quality factor at 1 hertz. At 1 hertz. So that we need to know. And so 1 by Q0 is the attenuation at 1 hertz, or it is called Q0 inverse. This is the attenuation at 1 hertz. Attenuation at 1 hertz. Right? So that's your 1 by Q0. Okay? And then f to the power n, so that will be the 1 by f to the power n means f to the power minus n. So this f to the power so this n value can go from 0.2 to 0.8. So depending upon how you are trying to model it, so that's your particularly that particular place, you need to know this QF values, right? And that you can get it from the seismological observations at some of the points. So in general, it can go up to, the Q0 can be from, say, suppose 50 to might be 300 or 500 values, and the n value can go from 0 to 8, right? So that you can take depending upon your place. By seeing the sum of the observations, we can always calculate the Q0. So this Q0 path will be included, and that will be the path factor down. Okay, so next time we'll be doing the site, but next time. Yeah.